Let's talk about energy stored in a capacitor. So suppose we have an initially uncharged capacitor and we're about to connect it to a battery, maybe through a switch. Initially, the voltage across the capacitor, the initial, is equal to 0. And there's no charge on the capacitor initially either. Now, when I throw the switch, the capacitor will begin to charge up. Notice, when it's fully charged, the voltage, call it V final, is going to be equal to the voltage across the battery, and the charge on the capacitor will be equal to the charge coming from the battery, or we'll just write that as the capacitance of the capacitor times the voltage of the battery. But notice, what we can say the average potential difference as this thing is charging up, it goes from V0 to V, so we can write that the average potential difference is equal to V over 2. Or I can write that as Q over 2C. So the work I would need to charge the capacitor would be equal to Q times V over 2, or 1/2 Q squared over 2, I should say 1/2 Q squared over C. So this is the work needed to charge the capacitor. That's sort of a ballpark, back of the envelope estimate. We could do a more detailed proof. Suppose we said the following. Suppose that the charge, we have charged little q on the capacitor at some time t while the capacitor is charging. Well, at this point, the voltage on the capacitor would be equal to Q over C. If I want to transfer just a little bit more charge, suppose I want to transfer a little bit more charge dQ from the battery to the capacitor, the work I would have to do, this incremental amount of work, dW, would be equal to V times dQ, which I can write as Q over C dQ. And of course, if I want to find the total work I would have to do to fully charge the capacitor, I would just have to integrate. It would just be equal to 1 over C times the integral of from 0 charge to fully charged of Q dQ, which I could write then when I integrate Q dQ, of course I get Q squared over 2 times C, evaluated between 0 and capital Q, which is just capital Q squared over 2C, as we had said before in our sort of hand-waving argument. So this is going to work for any capacitor. Likewise, because we know that we can write C as Q over V, there are other ways of writing the work it takes to charge the capacitor, or the energy that is now contained in the capacitor. I can write it as 1/2 CV squared. I can also write it as Q, I can write it as QV over 2. All of these are equivalent to saying how much energy is stored in the capacitor. So for a given capacitance, the stored energy increases as the charge or the potential difference increases. Now there's a limit as to how much energy the capacitor can store. If I exceed that limit, there's going to be a discharge between the plates. And you'll see a spark between the plates of the capacitor. That's because you have too high a voltage between the plates. We can also look at it this way. There's probably a more far-reaching expression for the energy stored in the capacitor, and we can arrive at it this way. Take a parallel plate capacitor. It doesn't matter, but let's That's the simplest example. I can write the electric field between the plates of the capacitor as the voltage divided by the distance between the plates. I know the capacitance of the capacitor is epsilon naught A over D, where A is the area of the plates and D is the distance between the plates. I can put this together. I can say then that the energy stored in the capacitor I'll write as 1/2 CV squared, which I can write as 1/2 times E squared E squared, using the first equation, times epsilon naught A over D, which gives me 1/2 epsilon naught A, 1/2 epsilon naught E squared A D squared. Sorry, A times D. I can multiply area times the distance between the plates. That gives me a volume. So the energy per volume, what we often define as an energy density, little u, is equal to energy per volume, or 1/2 epsilon naught E squared. And this is a universal expression for the energy stored in the parallel plate capacitor, or any capacitor. And as you can see, the energy is actually stored in the electric field between the plates of the capacitor. So this is going to be actually, as we go deeper into the course, you'll see that there's a more far-reaching application than just capacitors for this expression, but it's a very good one. It's just 1/2 times a constant times the electric field squared for the capacitor. This is, as I say, going to be generally valid. So, and we will come back, when we do magnetic fields, we're going to see a similar equation for energy stored in an inductor, and it's stored in the magnetic field of the inductor. We'll have a similar expression to this. I'm going to change gears a little bit, and now I want to talk about ways that we can enhance the capacitance. Sometimes we want to be able to store more charge on a capacitor, and the easiest way to do that, given that you can't maybe make the capacitor as big as a city, and you can't reduce the distance between the plates too much, one of the things you can do, though, is to insert between the plates of a capacitor an insulating material called a dielectric. When I place that material in between the plates of the capacitor, that will increase the capacitance by a factor of what we call kappa. Kappa is the dielectric constant, and it's particular to whatever material you insert between the plates. Good examples of dielectrics would be mylar, paraffin. There are numerous other examples that we'll talk about. In some capacitors, even oil. So the capacitance will increase by a factor of kappa if I can fill the area between the plates with the dielectric. And what will happen then is the voltage across the capacitor will remain the same, the capacitance will increase, therefore the capacitor can hold more charge. For a parallel plate capacitor, the capacitance gets multiplied, so epsilon naught A over D gets multiplied by kappa, very simple. And then, as we've said before, we can't make D too small, or we'll have an electrical discharge between the plates. We call it dielectric breakdown. And so the way that we can enhance the capacitor is by putting in a dielectric. So they provide the following advantages. One, they can increase the capacitance. They'll increase the amount of operating voltage you use for the same charge. And it will provide mechanical support between the plates. So I can bring the plates close together and they won't touch because I'll have this insulating material in between the two plates. typical chart of dielectrics. Air, of course, has a dielectric constant of 1. Other substances, we have things like quartz and mylar, rubber, nylon, paper, paraffin. All these things are used, as well as things like Teflon and silicone oil. All tend to increase the capacitance of the capacitor. I can talk about different types of capacitor. Oftentimes we have a tubular capacitor that's cylindrically shaped. We can use a metal foil, interlace it with sheets of paraffin, which is a good dielectric, and roll it into a capacitor. This is a very common type of capacitor. Another type used for high voltage purposes are oil capacitors. So we have metallic plates that are interwoven with silicone oil. And those, as I say, are used in high voltage applications. Another type of capacitor you'll probably run across is an electrolytic capacitor. One of the things from a practical point of view, most capacitors you can insert in a circuit one way or the other. It doesn't matter how you connect it. An electrolytic capacitor is different, though. You have to be very careful and make sure you're connecting the electrolytic capacitor the proper way, because the charge is only going to flow, is only allowed to flow in one way. In this case, we use the electrolytic to store a large amount of charge at low voltages. We use some electrolyte solution that's good at conducting electricity. If I apply a voltage between the foil and the electrolyte, we get a thin layer of metal oxide formed, which will serve as the dielectric. And we can get large values of capacitance doing this because the dielectric layer is very thin. We can keep the plate separation very small. Both of those things will enhance the size of the capacitance. And then we come to this device, which is what we call a variable capacitor. Variable capacitors allow you to change the capacitance without changing anything else in the circuit. They use air as a dielectric. They consist of 2 interwoven sets of metallic plates. And you can get capacitance that go maybe from 10 to 500 picofarads. Oftentimes they're used in tuning radio circuits. So that's yet another type of capacitor. Now, in order to understand how dielectrics work, you probably need to take a course in solid state physics or condensed matter physics. But without doing that, we can still get a better picture of how dielectrics actually work by talking about them on a microscopic perspective, or in a microscopic perspective. To do that, though, we're going to have to define some terms. We've mentioned one of these terms before. That's electric dipole. We talked about finding the electric field and electric potential due to a electric dipole. I'm going to talk a little bit more about them. We've said that it's a positive charge and a negative charge that are equal, separated by some distance. In this case, they're calling it 2A. We define the dipole moment, P, not to be confused with momentum, P, dipole moment as the product of the charge and the distance between them. That's what we call a dipole moment. So in that case, it would have been 2A times Q for the dipole moment. Now, if I place the dipole in a uniform external field, now, let's see what happens. Remember, we're not talking about the E field that's caused by the dipole. We're taking the dipole and putting it in an external electric field. And suppose the field makes an angle theta with the dipole moment. So here's the electric field parallel, and I've got the dipole moment in this direction. What's going to happen is the net force on the dipole, of course, will be 0 because I have a positive charge and a negative charge, so they'll be equal and opposite forces. But those forces will produce a torque. It will cause a rotation of the dipole, and it will tend to rotate it in a manner that, so we can talk about a torque equal to the force times the moment arm times the angle between them, or in this case, it's going to be the dipole moment times the electric field times the sine theta. I can write that sine theta, of course, we can write that as a vector cross product between the dipole moment vector and the electric field vector. So we can write the torque as P cross E. By the same token, we can talk about the potential energy as a function of the orientation of the dipole, and we can write that as P dot E, or PE cosine theta, negative PE cosine theta, for the energy of a dipole. You'll see this for electric dipoles. More often, though, than this, you'll see this for magnetic dipoles. Those will be coming later on in the course. Well, speaking of dipoles, those of you who study chemistry know that there's such a thing as polar molecules versus nonpolar molecules. If I have a separation between the positive charge and the negative charge, the average position of the positive charge and negative charge, we say that the molecule is polarized. If they lie on top of one another, we call them nonpolar molecules. Good example of a polarized molecule, of course, is the water dipole. There's an angle of 105 degrees between the two hydrogens with respect to the oxygen and water. And you can see that the center of negative charge is very close to the oxygen atom, whereas the center of positive charge is directly in between the two hydrogen atoms, which of course gives me a polar molecule. So water is a really good example of a polar molecule. And so these can be modeled as electric dipoles. On the other hand, we can have a situation where we start with a molecule that doesn't have any polarization whatsoever, something where the charge is symmetrically distributed, but then all of a sudden put an E field present. If I put an E field going from right to left, notice what will happen. The negative charge will move in this direction closer to the positive charge, and that's going to induce a polarization in this molecule. Let's take it to an even smaller view. Molecules that make up the dielectric are modeled as dipoles. The molecules are randomly oriented in the absence of an electric field. But if I put them in the presence of an electric field, notice what will happen. These guys will align. All the positive charges will be aligned this way. All the negatives will be aligned this way. If my electric field is going, let's say I'm using a capacitor, the field is going in this direction, so all the positives are going to be into the right, and the negatives will move to the left. And as long as the temperature isn't too high, the electrical effect will be larger than the thermal effect. And so we'll have this degree of alignment of the molecule. So you have a polar molecule in that sense. So if I use molecules in a dielectric that are nonpolar, by inserting an electric field, I can produce some charge separation, induce a dipole moment, and it would be almost as though the molecules were polar. By the same token, I can do the following. Suppose I have an external field polarizing this, the dielectric in between the plates of a capacitor. Notice what will happen. The charged edges of the dielectric will act as a second pair of plates, producing an induced electric field in the direction that's opposite. So I'm inducing a positive charge in the dielectric on this side, a negative charge on this side, and so I have a field induced going from right to left, as well as a field going from left to right due to the capacitor. So that's just another example of how they work on a smaller, microscopic level. So the electric field due to the plates is directed to the right. It polarizes the dielectric. The net effect on the dielectric is to induce an electric field that points to the left. Now, if we take the dielectric out and put a conductor in, of course, the net field between the plates would be zero, as we would expect from our knowledge of electrostatics. That's all I'm going to say about capacitance today. We will come back to capacitors when we are finished with RC circuits, I should say, when we're finished with circuits of resistors, we will then study circuits that have both resistors and capacitors in them. And we'll talk about that later.